the Linux device model. So from this lecture onwards, let's discuss the Linux device model. First of all, what exactly is a Linux device model? The Linux device model is nothing but a collection of various data structures and helper functions that provide a unifying and hierarchical view of all the buses, devices, drivers present on the system. You can access the whole Linux device and driver model through a pseudo file system called sysfs, which is mounted at a root sysfs. Different components of the Linux device model is represented as files and directories through sysfs. So the sysfs exposes underlying bus, device, and driver details and their relationships in the Linux device model. So by using various data structures, the Linux device model binds all the buses, the devices, and drivers of the system through its various data structures. We are going to explore some of the data structures used in Linux device model in this section. So these are different components through which the Linux device model is realized. To represent a device, the Linux device model uses an instance of struct device data structure. To represent a device driver, the Linux device model uses an instance of struct device driver data structure. Basically, the Linux device model consists of lots of data structures through which the different components of the hardware and software is managed. A bus is represented by an instance of data structure struct bus type. After that, there are other kernel data structures such as kobject, kset, kobject type through which the whole Linux device and driver model is viewed. The goal of this section is to understand these components in subsequent lectures. Alright, so now let's understand what exactly is a device in Linux. That is, how to represent a device in software. Note that in Linux device model, anything which can be represented by an instance of the data structure struct device is a device. Similarly, anything which can be represented by an instance of the data structure struct device driver is a driver. So a device is represented in software by struct device, and a driver is represented in software by struct device driver. Let's consider an example of a platform device, such as, let's say, an ADC device. Here, ADC is a device, right? And we can represent this in software using an instance of struct device. If you just look at the explanation of struct device, it says, at the lowest level, every device in Linux system is represented by an instance of struct device, and it also says that the device structure contains the information that the device model core needs to model the system. So most subsystems, however, track additional information about the devices they host. As a result, it is rare for devices to be represented by bare device structures. Instead, the structure, like kobject structures, is usually embedded within a higher level representation of the device. If you consider this device at bare minimal level, it is represented by an instance of struct device. That's fine. But this device actually belongs to the platform subsystems of the Linux. So according to the Linux, this device is connected to the platform bus, hence you can call it as a platform device. So the high-level data structure to manage this device will be struct platform device. You can see that struct device is embedded within struct platform device. Now there are two things. So this higher level structure, that is struct platform device, is subsystem specific. The member elements of the struct platform device, it carries subsystem specific information, and the information which is contained within struct device is subsystem independent. And if you look at struct device closely, it carries various member elements which help Linux to model the whole device topology. So, a struct device has a pointer to its parent, It has got a pointer to its associated device tree node. It has pointer to its bus type. The pointer to the struct bus type on which the device sits, and it also has got the pointer to the struct device driver, that is pointer to the driver data structure who is managing this device, and it also has pointer to the driver specific as well as platform specific data. Now let's consider this example. Here RTC is a device which is connected to the I2C bus. So at the bare minimal level, it's just a device which can be represented by an instance of struct device. But this RTC device belongs to the I2C subsystem. So as per I2C subsystem of Linux, we call it as I2C client device. Even though it's a platform device, its subsystem is different. So RTC here is an I2C client device. So as per its subsystem, it is actually represented by an instance of struct I2C client. Here is the structure, struct I2C client. Again, here you see struct device is embedded inside this structure as well. So the member elements of the struct I2C client represent information which are specific to the I2C subsystem of Linux. Now let's consider this hierarchy here. This is exactly how the I2C based RTC is connected to the system. Here you see two devices. One is I2C host controller of the SoC, and another device is an RTC device. Host controller device is an on-chip device, and RTC is, let's consider, off-chip. So here I2C host controller controls the I2C bus on which various peripheral devices are connected, such as RTC. In this case, the I2C host controller is represented by an instance of struct platform device. Here the I2C host controller device is a platform device because it is connected to the platform bus, and RTC is an I2C client device and it is represented by an instance of struct I2C client. So there are two subsystems here. One is the I2C subsystem and another one is a platform subsystem. Now there will be two drivers to take care of these two devices. The first one is I2C host controller driver, which is a platform driver, and the second driver is to take care of I2C based RTC device, which we call I2C client driver. So the driver of this I2C host controller is represented by an instance of struct platform driver, and the driver of this RTC device is represented by an instance of struct I2C driver. And you see here both of these structures embed struct device driver structure, because at the bare minimal level, every driver in Linux device model is represented by an instance of struct device driver. So now if you are wondering where exactly is a I2C host controller driver, now let's get into the Linux source tree and let's go to the drivers, and here let's get inside I2C and let's get inside buses here, and you see I2C OMAP. Let's consider our SoC, and you see I2C OMAP somewhere here, right here. So this is a I2C host controller driver for OMAP based SoCs. Come at the end, here you see this driver is registered as platform driver. This driver is represented by struct platform driver. Now let's check the driver of off-chip RTC device. Let's again visit drivers and just get inside RTC. Here it is, RTC, and let's explore this RTC DS1374, which is a famous RTC chip we use with Arduino and all. Here it is. This is the RTC client driver for DS1374 real-time clock over I2C, and this is actually, we call it as a I2C client driver. You see here, this is actually registered as struct I2C underscore driver. So you can see that it is registered like that. It actually registered to the I2C subsystem, whereas platform driver register, that's a registration to the platform subsystem. And if you just check this I2C driver, and it has got all these member elements related to the I2C subsystem, and you see here it embeds struct device driver, that is a subsystem independent structure. So like that, the devices and drivers are represented in a Linux device model. There is also one more RTC device, that is DS1347. So this is actually SPI compatible. It is not based on I2C, and you see here this driver is represented as struct SPI driver. So you can call this driver as SPI client driver because the bus is different here. This device is connected over SPI bus. Now in this lecture, let's understand K-objects. K-object stands for kernel object, which is represented by struct K-object. K-objects are the fundamental building blocks of Linux device and driver hierarchy. K-objects are used to represent the containers in the sysfs virtual file system. K-objects are also used for reference counting of the containers. So you can find the K-object structure in include kobject.h file, and here you can see a member element called kref. Kref is actually used for reference counting of containers. I'll talk about containers in a moment, don't worry. The K-object has got its own name, it has got its own type and parent pointer to view the Linux device and driver hierarchy. Using K-objects, you can add attributes to the container which can be viewed or altered by the user space. In future videos, we'll see how to add attributes to the K-objects for reading and writing purposes. The sysfs file system gets populated because of K-objects. Sysfs is a user space representation of the K-objects hierarchy inside the kernel. So now what are containers? So we saw the word container. What exactly is a container? Remember that K-objects are rarely or never used as a standalone kernel object. Most of the time, they are embedded in some other structure that we call as a container structure. Some example of container structure could be struct bus, which represents a bus, struct device, which represents a device, and struct device driver, which represents a device driver in the Linux device and driver model. There are many container structures, but these three are the major structures what we use frequently. That's why K-object is embedded within these container structures. So the container structure's embedded K-object enables the container to become part of an object hierarchy, which you'll see in the future videos. So in the previous slide, I said the K-object is used for reference counting of the containers. Most of the time, K-object is not used as a standalone kernel object. It's basically embedded within some larger kernel objects which represent kernel resource. So the reference count variable inside the K-object tracks containers usage. You see here, struct device is a container and K-object is embedded within it. Inside the K-object, there is a reference counter, kref. So this reference counter tracks references made to this struct device object. When the K-object is initially created and initialized, the reference count, which is actually an atomic counter, is initialized to 1. Whenever any Linux kernel core or subsystem makes any references to this kernel object, its reference count is incremented by 1, and the reference count variable is decremented by 1 when any kernel code or any subsystem no longer needs any references to this kernel object. So whenever the kernel object is being used, its reference count is incremented, and whenever it is not used, the kernel code actually decrements the reference count. So as long as the reference count variable is non-zero, the k-object continues to be exist in the memory. Thereby, the container also exists in the memory. When the reference count becomes 0, it indicates that the kernel object is no longer required and the memory associated with that k-object can be freed. So, when k-object's reference count value becomes 0, the release method of the k-object gets called, where you can free the container if the memory for it allocated dynamically. Actually, you don't find the place to initialize release method in the k-object structure. It's actually inside the k-object underscore type structure. So when the kref becomes 0, the release method gets invoked, where you can do some cleanup procedure. You may remember in our earlier example of platform driver, we wrote a device setup code where we implemented a release function, isn't it? Actually, we didn't do anything there because the container object that is struct platform device was not dynamically created. If it was allocated dynamically, then we would have freed the memory in the release function. So that's why k-objects are the basic building block of Linux device driver model. So they are majorly used for reference counting of the containers. And in future lecture, we'll also explore how k-object and sysfs are related. Actually, k-objects are used to represent the containers in the sysfs virtual file system. We'll explore that in future videos. So in this lecture, let's explore k-object type and k-sets. First, let's understand what exactly is k-object's type or type of a k-object. Type of a k-object is determined based on type of the container in which the k-object is embedded. For example, if you see this image, there are many k-objects, but all these k-objects are embedded in a container of same type. The container type is struct device. So that's why we can say that all these k-objects are of same type. Now, the type of a k-object is controlled using the structure called struct k-obj underscore type. This structure is used to define the default behavior for a group of k-objects of same container type. The behavior is nothing but attributes, the manifestation of attributes. We'll see attributes a little later. So let's understand the significance of this structure, struct k-obj underscore type. Struct k-obj underscore type object, or simply you call it k-type object, is an object which defines the behavior for the container object. Behaviors are manifested in terms of attributes and file operation methods that handle those attributes. The k-type also controls what happens to the k-object when it is created and destroyed. Every structure that embeds a k-object needs a corresponding k-type. So if you see here, instead of each k-object defining its own behavior, the behavior can be stored in a k-type, and k-objects of same type point at the same k-type structure, thus sharing the same behavior. The default behavior is first defined in the k-type object, and every k-object's k-type field will be initialized to the k-type object. Thus, k-objects of the same type share the common behavior extended by the k-type. So it's like that. The concept of k-type is to share the common behavior among all the k-objects. If you want to assign a type to your k-object, then you have to create an object of type struct k-obj underscore type, and you have to initialize the k-type field of the k-object. That's how you assign a type to your k-object. So k-object type structure has got some important fields. The first one is release method. Each k-object doesn't have its own release method. So the release method is actually provided by k-obj underscore type object. When the k-object's kref reaches 0, that is, the reference count reaches 0, the kernel calls the release method by referring to its type field. And in the release method, you can clean up the resources what you have claimed, something like below. So here, when the kref reaches 0, the release method of the kObject gets called, and kernel provides the kObject whose kref had reached 0. So you can use the container of macro to get the kObject's container object and free the container objects or its associates if the memory is allocated dynamically. So other two important fields of this structure are sysfs_ops. Sysfs_ops points to sysfs operation structure, which actually lists the methods to operate on the default attributes created for the kObject of this k-type. And one more important field is default_attributes. It's a pointer. So the default_attributes pointer is a list of default attributes that will be automatically created for an kObject that is registered with this k-type. Actually, I have a separate video which explains attributes, how you can create the attributes. So attributes of a kObject is nothing but sysfs files which gets created on behalf of a kObject. Those attribute files are used to share data with the user space. So we'll see how to create our own attributes in future videos. That's about struct kobj_type. So now let's explore ksets. A kset, as its name indicates, it's a set of kObjects of same type and belonging to a specific subsystem. Basically, kset is a higher level structure which collects all lower level kObjects which belong to a same type. So see this image. Every kObject has a parent field, and the parent field of every kObject is pointing to the parent field of the kObject which is residing in the struct kset. Struct kset also has a kObject embedded within it, and the parent fields of all kObjects, they point to parent field of the kObject of the kset. That's how Linux actually builds a hierarchy. So kset actually collects all the kObjects which belong to a same type. What this signifies is that kObject of the kset is parent of all these kObjects of same type. Using this model, the Linux maintains the device and driver hierarchy in the sysfs. Kset is represented by struct kset, and it is concerned with aggregation and collection of kObjects of same type. It can be thought of as the top level container class for kObjects. So the list field of this structure is a linked list of kObjects included in the kset. And the directory associated with these kObjects always appear in the directory of the parent kObject in the sysfs. Now let's explore the directory structure. Let's take an example of some directory structure of the sysfs. Now you may be familiar with this path in the sysfs directory, sys devices platform. This is a place where you can see all the platform devices of the system. Whenever you add a new platform device, it actually shows up in this path, sys devices platform. How does that happen actually? So that means the Linux device and driver model, it exports all the devices and drivers, bus details to the user space through the sysfs directory. So by going through various locations in the sysfs directory, you can fully understand the driver model of the system, the number of modules which are presently active in the system, the relationship between devices and driver classes. So various details you can gather by going through various locations in the sysfs. This is one such location where you can investigate the platform devices which are present in the system. The Linux is able to supply all this information via sysfs is because of the kObjects. Whenever you add a platform device, it actually shows up in this directory. So that's because of KObject. Why? Because a platform device has an embedded KObject, isn't it? Struct platform device has struct device embedded, and struct device has KObject. Because of this KObject, a directory actually appears in the sysfs. All these entries, what you see here, it's because of KObject. So all these KObjects, what you are seeing here, is of same type because the container of them is struct device or struct platform device, isn't it? All these KObjects are of same type. And remember that all these directory entries is because of an individual KObject. So now you can see the relationship between KSet and the KObjects here. As I said, all these KObjects are of same type, and this entry is because of a KObject present inside the struct KSet. The platform directory is because of this KObject, and the individual entries what you see inside that directory is because of these KObjects. It's like that. So this KSet and its associated KObjects, they belong to this subsystem, devices subsystem of the Linux device and driver model. That's the relationship between KObject and KSet. So if you go inside one of the KObject, here this is a KSet, and this is one of the platform device that is represented in sysfs because of KObject. If you go inside that KObject, you see various files here, and you see various symbolic links. So these are called as attributes. I mean, who created this? All these, they got created when you registered a platform device. The platform device registering procedure created some default attributes for the KObject. Attributes are nothing but files. They actually reveal some information to the user space. These are called as default attributes, what you see inside this KObject, and you can even create your custom attributes. We are going to explore that later. So inside a KObject, you also see one more KObject here. This is one more folder. Whenever you see a folder in the sysfs, that's because of KObject. That's why you see one folder here or directory, and that is because of a KObject, and this KObject is actually child of this KObject. It's like that. So now let's explore more. Here I am in the sys directory, and let me just go inside the bus subsystem. Basically, these top level directories under sys are actually different subsystems like bus subsystem, the device subsystem, the file system, block subsystem, etc. If you go under bus and if you just do ls here, you see different types of bus types. Like you can see here, there is a bus type SPI, I2C, MMC. It even has a platform bus. These are all different bus types. So you can call it as I2C subsystem, platform subsystem, like that. Let's get inside I2C, for example. Here, this is actually a subsystem. This is also a subsystem. And if you just do ls here, what you see here is a KSet. This is a KSet of devices. So this is a KSet of drivers. All these are attributes because these are actually files. Now let's get inside devices. So now you see here, this is a KSet. Here this is a symbolic link actually. A symbolic link which is pointing to the actual device, which is actually a PCI device. Basically, it is pointing to the sys devices path. The exact device is right here. So you can call it as an attribute here. That means these are 4 I2C client devices which are present on the system. And after that, if you go inside I2C0, so now you see here, this is a KObject of a KSet, actually belongs to the I2C subsystem, and it also lists a couple of attributes here. So all these are actually attributes. whereas this is attribute of type symbolic link, and this is a K object, another K object, which are children of this K object. Let's go back, and you also see another K set here, drivers. Now if you get inside drivers, and these are different I2C client drivers of the system, which are there on behalf of different I2C client devices. And if you go inside any directory here, and all these are actually attributes of this K object. This K object represents an I2C client driver. So you can even go to the platform bus, sys platform bus, and if you do ls-l here, and you get drivers, you even get devices, and you see here, actually this is our platform device, PC Dev B1X, something like that. If you just do ls-l, you see here, this actually points, basically it's a symbolic link which actually points to the actual device. Actual device you can find in sys devices platform. This is a platform device. This is just a symbolic link which points to that actual device. If you go under sys bus platform drivers, and you see our driver here, right? This is our driver. If you go inside that, and if you do just ls-l, so you see here, all these are different attributes. All these are attributes, and this is also attribute of type symbolic link. Who created all these things? So all these got created when you register your platform device or a platform driver. The subsystem actually creates all these default attributes. As I said in the previous lecture, you can even create more attributes here. For example, let's say you want your driver to reveal some driver specific information to the user space, then you can create more attributes here. That's what we call the attributes of the K object. Basically, this is a K object. This is a K object, and this is a K set, and these are all nothing but attributes of the K object, which reveals some information to the user space. Basically, in this case, this is a driver, a platform driver, which says that it actually manages all these devices, and the place of the actual device is actually under devices platform. So you can understand something like that. In this lecture, let's explore sysfs and creating K object attributes, are also called as sysfs attributes. First of all, let's explore what exactly is sysfs. Sysfs is a virtual in-memory file system which provides a representation of the K object hierarchy of the kernel. In the previous video, you saw, in the sysfs, each directory is because of K object. Basically, the whole sysfs is collection of K objects. The collection of K objects actually reveal the hierarchy of the Linux device and driver model of the system. So the sysfs actually provides complete topology of the devices and drivers of the system in terms of directories and attributes. Sysfs provides attributes to help user space application to interact with devices and drivers. The sysfs also provides standard methods to access devices using classes. If you want to have the sysfs support in the kernel, then make sure that the configuration item config_sysfs is defined in the kernel configuration. Actually, you need not to worry about this because it is enabled by default. So if you don't want sysfs support, then you can disable it by disabling this configuration item. So you can also mount the sysfs to root sysfs by using this command if it is not mounted. The whole kernel documentation about sysfs is available at documentation file systems sysfs.txt. Most of the information in this section is taken from sysfs.txt kernel documentation. Basically, in this video as well as in future videos, we are going to understand how to create our own KObject attributes for the devices and the driver. So KObject attributes are also called as sysfs attributes. These two terminologies we use interchangeably, sysfs attributes or KObject attributes. The meaning of KObject attributes means attributes that are created under a KObject. First of all, what is a KObject attribute? KObject attributes are regular files or symbolic names that appear in sysfs KObject directory, and they are used to expose details about KObject's container to user space. In short, KObject attributes are files through which device or driver data can be exposed to sysfs so that user space application can view or modify it. So in the earlier exercises, we actually created a class under sysclass, isn't it? The class was pcd_class. This we created using the function class create. And under that class, we actually created 4 devices. These devices we actually created using the function device create. And if you get inside one of the device, and if you just do ls-l here, you can see that this device actually reveals lots of details. Here you see 2 regular files, dev and uEvent. These are actually attributes which got created whenever you created a device using the function device create. Here this attribute is a regular file and you can read that file. This attribute actually reveals the device number of this device, and also the uEvent attribute actually reveals the major number, minor number, and the device name. This attribute actually helps the udev to create the device files under the dev directory. Now, apart from that, there are also some symbolic attributes. These are symbolic attributes, and the significance of this is actually this symbolic attribute is pointing to its parent device. It says that PCDAV A1X is a parent device of this device. This is a device which got instantiated from the device setup code or from the device tree. Because when we used device create function in our code, we actually mentioned the instantiated struct device as a parent for the device create function. So that's why you see this entry here. This is pointing to the parent device. And this is one more KObject which got created under this device. And if you go under this KObject here, and you see various attributes which are related to the power. These are all regular files, and you can read those attributes. When you read that attribute, it will reveal some information to the user space. So our goal in this section is to create some custom attributes, something like this, for our devices. So in the next lecture, we are going to do an exercise. The exercise is about creating custom attributes of a device. We have a device private data and we have device platform data. The platform actually provides all these data: size, permission, and the serial number. So in this exercise, we are going to create 2 sysfs attributes. The first attribute is max_size, and the second attribute is serial_num. Max_size, through this attribute, user reads or changes the value of the size information. From the user space, the user can change the value of this size information of a device using this attribute max_size. And its mode is word read and owner write. Anyone can read this attribute, but only owner can modify this attribute. We have to configure the mode to this attribute. How to do that, we'll see later. And the next attribute we are going to create is serial_num. It is a read-only attribute. So anyone can read this attribute. Through this attribute, user just reads the serial number of the device. In the next lecture, let's see how to create the sysfs attributes. We have to explore some data structure for that, and we'll see that in the next lecture. Hey, welcome back to the lecture. In this lecture, let's understand how to create the sysfs attributes, or you can also call it as k-object attributes or sysfs files. Sysfs attributes are represented by the below structure. In order to create an attribute, you should make use of this structure which is provided under Linux sysfs.h. Here it has two important fields, name and mode. Here you should mention the name of the attribute. This name will show in the sysfs k-object directory as attribute's name. And what is the access mode of that attribute you can mention here. So this mode actually controls the read-write permission for the attribute file from user space programs. Let's understand what are the most commonly used modes to access an attribute. You can make it as word read-only. That means anyone can read it. It's just a read-only item or attribute. So if you want to make an attribute just read-only by anyone in the world, then you can use this mode s_IRUGO. So it is actually called word read-only. So meaning anyone can read it. No root permission is required. Or you can make it as this mode. This mode means only owner can read it. Owner means whoever created that attribute only read it. That's called owner read only. Or you can use this mode. So anyone can read it, but only owner can modify it. Word read and only owner write. These are some important modes what we use in order to access an attribute. These macros you can mention here in the mode field of an attribute. So in our exercise, we are creating two device attributes. The max size attribute will be with mode this one, word read, and only owner can change it. And the serial number attribute is word read only attribute. So we'll be using this macro in order to set the mode. Now let's move forward. These are the APIs to manage the sysfs files or attributes. So you have got one kernel helper function to create it, create a file, sysfs create file. Look at this function. It's very easy. You just have to mention the destination k-object's address. So remember, k-object is nothing but a directory in the sysfs. Just mention the address of the k-object and just mention the address of the attribute structure. And this function will create the attribute under this k-object directory. So you can manage attributes using many helper functions which are available in sysfs.h. You can even change the mode using sysfs change mode. Alright, we'll see how to use them when we start coding. Let's move forward. Once you create the attributes, why do you create the attributes? You create the attributes to reveal some information to the user space or to get some information from the user space to configure your device or to configure your drivers. That means now you have to provide the file operation methods for those sysfs attributes. Once you create a sysfs files, you should provide read and write methods for them so that user can read value from the attribute or write a new value to the attribute. If you see struct attribute, there is no place to hook your read and write methods for an attribute. For example here, so there is no place to hook your methods. That's why we have to use slightly different version of struct attribute called struct device attribute. So struct device attribute is more suitable because this is a case of creating an attribute for a device. So we are creating attributes to control our device. That's why it makes more sense to use struct device attribute. It is little higher level of struct attribute. You can see that the struct attribute is actually embedded inside the device attribute. The only difference is The device attribute is actually a wrapper for struct attribute along with the function pointers to hook your file operation methods. So that's why use this structure if your goal is to create attributes for a device and to provide show and store methods. Show means show the attribute to the user space. Store means take the value from the user space and store it into the attribute. So we'll explore more on show and store later. Let's move forward. Basically what you should be doing now is you are going to create variables of this structure type. We have got two attributes, so you should create two variables of this structure type. Now let's explore creating device attribute variables. There is one shortcut to create variables of struct device attribute, and the shortcut is to use the macros given by the Linux device.h header file. So instead of manually creating variables of struct device attributes and initializing them, use the device attr macros given in the Linux device.h. These macros you can find in the device.h, and here it is. Let's say you want to create a variable for struct device attribute, so with some mode and with some name. Then you can just use this macro. It will create the variable for you. Basically, if you just see this macro, it actually manifests into the struct device variable. Basically what it does is it actually attaches the name what you have mentioned here to the variable name here. That's why you can use one among these macros. If you want to make your attribute read write, then you can use device attr read write. If you want to make your attribute read only, then you can use this macro. For write only, you can use this macro, like that. So the use case is something like this. Instead of creating a variable and initializing the name, initializing the mode, and initializing the show and store method, something like this, you can just use the device attr macro and just mention the name of the variable here and mention the mode and mention the name of the show and store methods here. It will create the variable. So we'll see how to use these macros when we start coding. Before exploring show and store methods, now let's get into our editor and let's start coding for this exercise. So I'll see you in the next lecture, and after that we'll explore show and store methods. So now let's get into our custom drivers folder, and here now let's create one more directory. Let me call it as 006 pcd. I call it as sysfs. Now let's get into that directory. Now let's copy our previous exercise because we are going to modify that driver itself. Copy 005 dt pcd platform driver underscore dt.c. Let's copy here, and also we need the platform.h, and after that we need the makefile. So I just copied makefile, pcd platform driver dt, and platform.h. So let me just rename this file as pcd platform driver dt underscore sysfs. So it just signifies that we just added sysfs support. Fine. Let's edit the makefile underscore sysfs. So we just created this file, make this sysfs. Let's edit this file. Here this driver file has too many codes, isn't it? So now let's simplify it. What I'm going to do is I'm going to create more source files, and we will transfer some of the code into other source files. Otherwise we may get confused. That's why what I'm going to do now is here I'm going to create one more source file called pcd underscore system calls, something like that, syscalls. And after that, I will create one header file, pcd platform driver dtsysfs.h. That's sufficient. Let me open pcd syscalls.c. What I do here is I'm going to transfer all these system call handlers, our driver methods, to this file. I'm going to cut all these codes from release to lsig and this check permission as well. I'm going to cut it and I put that in this file. And after that, all these header files and these structure definition we can move to the header file. I just open the header file what I created, .h file. Here I'm going to transfer all these details. So I'm going to cut this and I'm going to paste that in sysfs.h. And after that, I'm going to cut these structures as well. Cut it and move to the .h. After that, let's go back to the .c file. And so that much is sufficient. The .c file now has only the driver's private data variable, the file operations initialization, and it has got remove function, probe function, and after that, the driver init function and the cleanup function. All the system call handlers I actually moved to the syscalls.c, and some structure definitions I moved to the .h file of the driver. So in the .c file, now let's include the driver's header file. Include pcd platform driver dt sysfs.h. Just include this and include this header file in syscalls.c as well. And for this header file, let's give the include guards. If not defined, pcd platform dt sysfs underscore h, define it. And at the end, let's use endif. Let's save this, and let's save this as well. So now let's go back to our command prompt. Here we just created syscalls.c and the driver's header file and the driver source file. Let's edit the make file to compile all these different source files. Here we have to slightly change this make file because we are compiling more than one source file. Here, first of all, let's give one name for our final .ko file. I call it as pcd underscore sysfs.o. This is a final object file. When you compile this project, pcd underscore sysfs.ko will be created. The dependencies for this object file we have to mention now. That you can mention by using this name. Just use this name pcd underscore sysfs, and after that you have to use hyphen objs plus is equal to, and now mention the dependencies, the dependent object files. We have got two source files that you have to mention here. That is pcd platform driver dt underscore sysfs.o and pcd underscore syscalls.o. So these are the dependent object files to create the final object file, that is this one. Let's save and exit, and let's do make host. There's a problem. So that seems to be some problem. Let's find out. Now let's see the .c file. So there is one problem. In the .c file, we actually initialized this file operation structure, and we initialized these function pointers with these methods. These methods are not available in this .c file. They are actually moved to pcd_syscalls.c. That's why there are errors. Now you have to give the prototype of these methods. That's why. So just copy these names, these function names, into sysfs.h. In the sysfs.h, let's write the prototypes of those methods. Just copy this lseek, paste here and give semicolon. So now let's save this and let's run the command make host. So it builds fine. Complete up to here, and I'll see you in the next lecture. Now let's open the driver file. So now first let's create two variables of struct device attribute that we can do here at the beginning of this driver file. I would do after this file operation structure. Create two variables of struct device attribute. So for that, as I said in the previous lecture, we can make use of these macros. I will use device attribute macro. Let's go here. So let's create the first one. You can use the keyword static to make it private to this file. Device attr, and for this you have to first mention the name. Our first attribute is max size. That's a name. After that, you have to mention the mode. For the max size, we are going to use this mode. After that, you have to mention the show method and the store method. Let me write the show method as max size show and max size store, and end this statement by giving a semicolon. We just created one variable. Now let's copy this, and our next variable is serial number, and its mode is, or you can simply use these macros, read only, read write. So these macros, if you use these macros, then you can get rid of mentioning the mode. You can also use that. So here the mode will be yes_ir_ugo, because this is a read only attribute, and the show method would be serial number show, and here there is no store method actually, that's why this will be null. So we just created two variables. Let's define these show and store methods. To get the prototypes of these methods, you can visit the device.h file. Here is the struct device attribute structure, and these are the prototypes for the show and store methods. Let's just copy this, and you can implement the show and store methods above these device attribute variables. I would paste here. Let me align this. The first one is show for max size. Max size show. So this is the first function. Now let me just, for timing, let me just return 0. And we have got one more show, right, for the serial number. Let me copy and paste. This is for the serial number show. And after that, we have got one store, that is max size store. For the time being, let me return 0. Later we'll understand how to implement these show and store methods. And after that, let's create the sysfs attributes in the sysfs directory. For that, we have to explore the attribute creation helper functions of the kernel that you can get in sysfs.h. Let's go to the sysfs.h right here, and Let me just explore sysfs create file. So here it is, sysfs create file. Here it is. All you need to do is, for the sysfs create file, you have to mention the key object and the attribute. Let's use this sysfs create file. Let's go to the probe function first. Let's start coding from here. So here we actually do the device create, isn't it? Basically, we first create the class, and inside the class we actually create the device by using device create. Inside this device, let's keep these sysfs attributes, whatever we are going to create now. That's why you have to use this pointer, because this pointer is a reference to a device which got created in the sysfs directory. Let me create one helper function here, pcd sysfs create file, something like that. I just create one helper function here, and let me catch the return value of this helper function. So if the return value is negative, I just conclude that the sysfs file creation has failed. What I would do is I would just destroy the devices. Device destroy. And just return the error code. First, let's implement this. Here I just pass this pointer, because as I said, this pointer gives me the reference to the device what I just created in the sysfs. I just pass that pointer here, pcdrv underscore data dot device pcd. Let's implement that helper function here, or I would create that here on top of this remove function. Int pcd sysfs create files. What we are going to receive is struct device pointer, device dev, or I would write pcd dev, something like that. So here I'm going to use sysfs create file. Let's copy that, sysfs create file. First thing what you should mention is key object, address to the key object. Key object I can get from this structure, address of key object, pcd dev of kobj, because every struct device has an embedded key object. The next argument is address of the attribute variable. So we actually used this macro device attribute. When you pass through the name here, it actually creates a variable name of this type. It actually attaches that name to this word dev underscore attr. That's why this is actually the variable name, dev underscore attr underscore max size. That's a variable name, and you have to pass the pointer of the attribute structure, so dot attr, because device attribute has struct attribute. Pointer to this variable you have to pass. That's why I used dot operator here. So you have to send the address of it, ampersand. Int return is equal to. So now let's see what is the return value of this function. This function calls this function sysfs create file underscore ns, and this returns what this function returns. Let's check this. Here it actually returns integer, and I think it returns an error code. So it returns error code or 0. We have to return that. Let's do one thing. Here if return is non-zero, then just return. I think we can optimize this using a different sysfs file creation function. So I will show you that later. But for a time being, let's create the attributes one by one using sysfs create file. Let me repeat this for the next attribute. The next attribute is attribute serial number. Just return. I think here this return statement is not required. So just return RET. Or you can simply write something like this, a return. Let's remove this. So we actually created two sysfs files. Let's go back to our pro function and let's fix this. If this return is negative or non-zero, just do the device destroy, because we cannot proceed because we couldn't able to create our attributes, isn't it? Device destroy I can copy from here. So device destroy we actually do like this. Mention the reference to the device and the device number. Let's compile this. Compilation is fine and complete up to here, and in the next lecture let's test this. Let's see whether our attributes are really getting created or not. I'll see you in the next lecture. So now let's test this. Before testing, make sure that you remove all the previously loaded drivers. Make sure that other drivers are not exist, otherwise it may lead to crash. And now first let's load the device setup code, because we have to invoke our pro function. From the pro function itself, we actually initiate creation of sysfs attributes. That's why I'm going to my earlier project 004. So here we have got device setup code. Let me just do a make host here and let me load first PCD device setup code. Let me go back to my current project, insmod PCD sysfs.ko. Let's do dmessage, and here you can see that the pro function was executed and the device instantiation was successful. All these are previously implemented codes, isn't it? The change was to create the attribute files. Let's check that. Let's go to sys class PCD class. These are the device creations. Let's get inside one of the device, and here it is. These are the attributes created: max size and serial number. So now the user can investigate this file to understand what's the maximum size of the device and the serial number of the device. For that, we have to implement the show and store methods. We haven't implemented them. That's why you cannot read or write into these files. Complete up to here, you must be able to see these files in the device directory here. You can go to any device. For example, if you go to PCD dev3, this also shows max size and serial number attribute. You can add more attributes. As I said, I will leave that to you. You can add a pre-space attribute or any other attribute. And in the next lecture, let's explore how to read and write into these attributes. I'll see you in the next lecture. In this lecture, let's understand show and store methods. The show method is used to export attributes value to the user space, and the store method is used to receive a new value from the user space for an attribute. First, let's explore the show method. This is a prototype of the show method. This function gets invoked when user space program tries to read the value of an attribute. This function will be called by the kernel whenever there is an attempt from the user space to read the attribute. Actually, kernel passes the pointer of the struct pointer to the device, and it also gives a pointer to the attribute and also a buffer. What you should do in show method is you must copy the value of the attribute into the buffer pointer. Show means you are showing it to the user space, so that's why you have to copy the value of the attribute to this buffer. Note that Buffer is not user level pointer. This is not a pointer which is given by the user space. It is not a user space pointer. This pointer is provided by the kernel buffer, so its size is limited to page size. For ARM architecture, it is actually 4 kilobytes, that is 4096 bytes long, this buffer. So while copying data to the buffer pointer, the size should not exceed 4096 bytes. So you have to keep this in mind while programming. To copy data into buffer, you can either use sprintf or scnprintf. So we'll see that when we code for this show method. Let's understand what's the difference between driver's read method and driver's show method. We also have got one read method, isn't it? A read method of the character driver. Please note that read method is used by the user space to read large amounts of data from the driver, whereas show method is used for reading a single value or an array of some values or data whose length is less than page size. For that purpose, we use show method. It's like a IOCTL kind of interface. Use the show method whenever you want to read a single value data, like a configuration item, something like that. So use the show method to read any configuration data of your device or driver. But to transfer large amount of data, you cannot use show method because its size is limited to the page size. You can use the read method of the driver in that case. What's the return value of the show method? The return value of the show method. Show method should return the number of bytes copied into the buffer or an error code. So now let's explore the store method. This is a prototype of the store method. This is similar to the show method, but the only difference is it has got one more argument here, count. This is invoked when user wants to modify the value of the sysfs file or the attribute. In this method, the buffer points to the user's data. But this is not a user level pointer. It's a kernel level pointer which holds the user data. And the count parameter is the amount of user data being passed inside the buffer. So the maximum amount of data which the buffer pointer can carry is limited to page size. The data carried by the buffer is null terminated. The data which is carried by this pointer is a null terminated data. That means the maximum useful data could be 4095 bytes. So store method should return the number of bytes used from the buffer. If the entire buffer has been used, just return the count argument. That's about store method, and in the next lecture, we will implement our store and show methods. I'll see you in the next lecture. String to a number. So string to long. This helper function you can get in Linux kernel.h. So all you need to do is you have to mention the string over here. The start of the string. The string must be null terminated, remember. And for the conversion, you have to mention the base here. So the number base to use. The maximum supported base is 16. If base is 0, then the base of the string is automatically detected with the conventional semantics. So if you mention 0 here, then the base is automatically detected and it will be stored in this result argument. Okay. So if the string begins with 0 cross x, so then the number will be passed as a hexadecimal number. Suppose if this string begins with 0, then it will be passed as an octal number, like that. Okay. So otherwise it will be passed as a decimal. That's why if you want automatic detection of the base, then you can use 0. Or if you are confirmed that the user is only going to send the decimal number, then you can also use 10 here. Okay. So if you use 10 here, then the string will be passed as a decimal number, and the extracted number will be stored in this result. So here you must give the address of the long integer where the result of the conversion will be written to, okay, on success. So it returns 0 on success or some error code if the conversion is unsuccessful. Alright, now let's use this kernel helper function in our store method. So I am in the store method now. So first of all, let me create long result variable, and after that let me create one more variable, return. So return is equal to k string to long. Okay, first argument is buffer. So now let's assume that user is always going to write into max size attribute with decimal data. So we can use the base 10 here, or you can also use 0, no problem. I would just go for 10 here, and after that placeholder, so that is the address of result. So if return is non-zero, then that's an error. Okay, return, just return here, return the error code. So if the conversion is successful, then you should place this result into device private data. So let's get the device private data. So let me copy this line, dev underscore data of pdata dot size is equal to the new size is result. So here you are changing the size actually, so that's why you have to reallocate the memory. So here you have changed the size information, so that's why you have to use k realloc to reallocate the memory with a new size. Okay, so that's why I would use here k realloc dev data of buffer, the new size. Okay, that is dev data p data size, and the flag gfp kernel. So this will be dev data of buffer is equal to, right? Alright, so this is actually data. So now here after that you should return count, okay, not 0. So because we have used all the data which is being passed in this buffer pointer, isn't it? So you can just return the count, no problem. Okay, now let's save and exit. Alright, so now let's do make host, and the build is fine. So let me remove the driver first. Okay, now let's load. Okay, so now first let's get into sys class pcd class. Let's get inside pc dev 0 cat serial number, cat max size. Yes, it's showing 512. Okay, so that's the maximum size of that device. So now let's change that. Okay, so let me pass 100 to max size. Okay, so it is successful. Now let's check. Yes, it got changed. So now let's change to 5. Okay, let's try to write some data. Dev pc dev 0, and you see it shows the right error because we actually changed the size to 5, isn't it? Alright, so that's about sysfs file creation and implementation of show and store methods. So we are going to play with these attributes more in future videos when we work with GPIOs and with the pin control subsystems. Okay, we'll see more examples, and in the next lecture I'm going to cover the attribute grouping. Okay, so I will cover that in the next lecture. So in this lecture, let's understand attribute grouping. In the previous lecture, you saw that we actually used a sysfs create file kernel function to create attributes of sysfs, isn't it? And we used it twice actually because we wanted to create two attributes. So instead of calling sysfs create file to create a sysfs file for every attribute, you can finish it off in one call using attribute grouping. So we are going to explore how to use this sysfs create group function. The function looks something like this. Here you have to mention the key object, and here you want to mention the pointer to the attribute group. So that means there is something called struct attribute group, which is used to collect all the attributes. So it does a collection. Now let's explore this struct attribute group. So struct attribute group, you can find this in sysfs.h, and here is a place where you can mention pointer to null terminated list of attributes. So basically it's a double pointer. So it indicates that you now need to create a pointer array of type struct attribute. And in that pointer array, you should collect addresses of all the individual attributes. And after that, you mention that a pointer array into this struct attributes variable. And after that, you can use this function to create all the attributes in one go. So now let's use this struct attribute group. So now let me take you back to the program. So here is a place where we created individual attributes, isn't it? Attribute variables, isn't it? So now we have to collect them in an array, okay? So for that, I'm going to create struct attribute. I'm going to create pointer array. So I would call it as PCD attributes. It's a pointer array. So in this pointer array, you have to collect the individual pointers to your attribute, okay, what you created here. So let's initialize this with an address of individual attributes, okay. So the first attribute we can get from here, right, max size. So dev attr max size dot attr. So because this is a variable of type device attribute, remember, and inside the device attribute there is a struct attribute, isn't it? So that's why I used dot attr. So if you are confused, you can see that in the device.h. Let's go to the device.h, and here it is device attribute, and inside that device attribute there's a attribute. So that's why I use dot operator, okay, comma. The next one is serial number. Yes, okay. So, and it should be null terminated. So the last entry, let's mention null, okay. So now let's create a variable for struct attribute group. Attribute group. So let me call it as PCD attribute group. So here you have to initialize the attrs field, okay, right. So you have to initialize this field attrs, pointer to null terminated list of attributes. So we created this null terminated list is equal to PCD attrs. That's it. And after that, here instead of using this twice, okay, so let me just deactivate this. What you can use is return sysfs create group, okay. So PCD dev the key object, and just mention the address of this attribute group, pcd attr group. That's it. Alright, so that is sufficient. Now let's save and exit. Make host. Alright, so there is a problem. Okay, so here I have to terminate this, okay, with a semicolon. Let's make host. Let me test this, okay. Alright, now let's test this, and you can see that we are still able to create these sysfs files. Great, so sysfs create group will be helpful when you have lots of attributes to be created in one go. So I hope you can reproduce this at your desk, and let me know if you have any questions, and I'll see you in the next lecture. In this section, let's understand GPIO subsystem